Okay, so on the agenda today, the first thing we're going to do is talk about sources. We'll take another look at sources of telemetry, right? Where we get data from. I will pull up that PowerPoint slide one more time that I like showing because I think the more you see it, the more used to that you'll get. I'll add to that a little bit. We'll take a closer look at Windows and specifically where you collect those different telemetry in Windows. And then we'll jump into Waza. We'll talk about writing decoders and rules. And I'll have a challenge for you guys to write your own custom decoder and custom rules. We'll talk a little bit about threat hunting in Waza, though this is not a threat hunting course, so we won't go super in-depth into it, but we'll go a little bit into it. And that's pretty much it. I think we'll call it a day there, although that might take us a while to get through. And then afterwards, if anybody, depending on when we finish and how late it is, if anybody wants to stay later, we might play another round of backdoors and breaches, which I think would actually be a great game for this group because we're basically doing defense stuff and learning about the defense tech stack. So that'll be optional and you can leave for that. Well, you can leave at any point. I'm not forcing you to stay here, but at least that'll be after the main presentation. Cool. So, where do we want to start? Let's start with, let me bring up that PowerPoint one more time just so that we have a little refresher because it's been 2 weeks. I now put it on my cheat sheets, I think. So a little bit of a review on where we get data from. 3 places. We have the network side of things, the system side of things, and the application side of things, right? And then from these different sources, those get fed into our SIM, which is kind of like our log aggregation and security tool. And that's where we would get, in most cases, that's where we would get our alerts that our analysts would take a look at and respond to, right? I want to dig into this one a little more. I want to dig into our Windows events and sysmon. Today we're going to be taking a much closer look at Windows and seeing what does Windows have that we can use to collect data about what's happening, right? So Windows has a few things that will be useful to us.
Before you proceed,
Go for it.
Could you elaborate on what you mean by telemetry?
Yes. So, telemetry is a fancy word for data or logs. So going back to this, everything that an attacker does creates some sort of, there's some sort of evidence of it, right, in our logs. Those logs are basically another fancier word for it is telemetry. Telemetry is data that you can use to see what's going on your system, basically. Yeah. So you can kind of replace telemetry with data. And I know I haven't used that term. I did mention it, I think, in the first day when I presented this, but I didn't use the term as often. So now I just kind of decided to start throwing it in there and using it, but just so you know. Basically, where do we get information from, right, in Windows? There are kind of 3 big things that I want to talk about. They're all separate, but they kind of work together. The first one is AMSI, or the Anti-Malware Scan Interface. This is an optional, I guess, feature in Windows that developers can use in their applications to monitor that application's memory while it's running, right? And it monitors that memory for indicators of something malicious. One program that uses AMSI is PowerShell, right? So if you were to spin up a PowerShell window that PowerShell window is going to be using AMSI. It's going to have this special AMSI DLL loaded into it, and it'll be monitoring the memory of the process. So if an attacker, for example, tries to download and load some malicious tool in memory, it would catch that tool. So an example of a hack tool is Rubius. If I try to load Rubius into memory, it would analyze the memory of that running process. It would say, oh, we've detected evidence of Rubius, and it would alert on that as being malicious, right? So that's AMSI. And why is AMSI important? Well, back in the day, attackers used to download tools to disk, right? So like, let's say I'm an attacker and I want to use a tool like Rubius to do Kerberos-related attacks, right? I gained access to your Windows machine. One thing I could do is I could download Rubius and then run Rubius from the disk, right? Like you would normally run applications. I would open up a command prompt or PowerShell window and do /rubius.exe, right? Now the problem is, because attackers were relying on disk a lot, defense solutions, like for example, even just the stock Windows Defender, they started really signaturing those files on disk. And we talked about that in the first presentation where we talked about malware and the malware analysis side of things. A lot of that is, like, for example, grabbing that exe, running it in a sandbox, dynamic analysis, or static analysis, looking for known malicious strings in a file. That's all because the file's on disk. So attackers, to adapt to that, have started using the disk less and less and only loading tools into memory, right? So you don't even have to touch the disk at all. There's a special class of executable files called .NET executables that can be loaded into memory without ever having to touch the disk. So you can actually download the data from somewhere external, like you can download it from online. You can load it directly into memory, and then you don't even have to touch the hard drive or the disk of the machine, right? So then it was necessary for the defenders to come up with something that can detect that in-memory malicious tool, right? And that's what AMSI does. So that's why AMSI is important. And any developer can choose to integrate AMSI into their application. But notably, PowerShell, which is very commonly leveraged by attackers, loads AMSI into it by default, right? And so AMSI just looks at the memory of that running process and looks for known bad strings that would correspond to hack tools, right? Or something malicious, and alerts on that or blocks that.
So if there is a new tool, Russia is going to be able to detect that, right?
Right. So that's similar to trying to evade disk detections. One way of evading memory detections is obfuscating or changing the code for the tool so that it's no longer known or signatured, right? And of course, I believe AMSI, just like regular Windows Defender, uses AI to maybe like train, and I actually could be wrong about that. I don't think it's just static strings. I think it is constantly learning and being updated by Windows too as tradecraft evolves. So it is a little bit of a cat and mouse game. But yes, if you were to develop a fully new tool that works differently than already existing tools, or maybe uses different code, then yeah, it might not get picked up by AMSI. That's a good point.
Even if the malware is encoded, will AMSI gonna spot it out?
Well, at some point, if malware is encoded, right, at some point you're going to have to decode it in order to run it, right? Mm-hmm. You have to give the computer the code so it knows what to run. So yes, you can transfer the code in an encoded format, right? But after you decode it, you'll have to decode it in memory, and AMSI might pick it up there.
Let's say if a malware is polymorphic or something like that. So it decodes and gets into the another shape or something like that.
In the end, there are instructions that your computer is going to have to run, right? No matter what. Like at the very end, if you're running malware, you want to run a set of instructions, right? Those instructions have to be those specific instructions. You can't just say, I'm going to, well, okay, maybe that's not entirely true. Like you can give different instructions to do the same thing sometimes, but in the end, you need those instructions. So in the end, that malware, no matter how you encode it or how you change it or how you mess with it, in the end, it's going to be converted to those instructions, right? Otherwise, it just can't run. Does that kind of make sense?
So it means you can signature the instruction.
What?
It means you can signature the instruction.
Yeah, so ideally you would signature the instructions. Now, where that gets difficult, of course, is a lot of the things that malware does is similar to a lot of the things that legitimate tools do, right? So it's hard to just say, like, if this function is being used, block it, because maybe there are some legitimate tools that are also using those functions. So you have to make trade-offs. This is good discussion, I think, though. Yeah, and I guess a useful reason for encoding malware is so that maybe when you're downloading it and somebody's looking at that network traffic, or if there's network traffic analysis being employed, it won't get detected there because it doesn't have the tools needed to decode it, right? Or if you were to download, or if you were to bypass, like download that malware on disk, right? Then encoding is useful because it's looking at those signatures when it's sitting on disk, and those signatures can remain encoded while they're on disk, right? It's only once it's in memory that it'll eventually have to decode it and run it. So, and that's why we have dynamic analysis in the first place for files that are on disk, so that it can actually try to run that file in a sandbox, perform the decoding, and then see if something malicious is happening. So far, so good. Questions about AMSI? All right.
So with the AMSI, can attackers disable, like when they're trying to get into a system, can they disable the functional?
They absolutely can. So both AMSI and ETW, we're going to talk about this more next week, but there's user land processes and kernel land. I guess I shouldn't say processes. There's the user land and there's the kernel land. The kernel land is anything that the operating system manages, and the user land is anything that that particular process manages, right? So AMSI and parts of ETW function in the user land in that actual process that's running. So there are ways for attackers to then patch or use hardware breakpoints. There are a couple different techniques for bypassing AMSI. We will actually be talking about that next week. So next week, today I'm kind of getting out of the way using Waza and writing rules. Next week, we're actually going to run a set of attacks, and we're going to see if we're able to detect it. One of those will be an AMSI bypass. So we're going to try different AMSI bypasses. We're going to try different ETW bypasses. But yeah, absolutely. Yes, an attacker can. And that's generally what an attacker would do. If an attacker gains access to a Windows machine, they're probably going to patch AMSI, patch ETW, disable script block logging, which is another thing I should add.
Some bullet points.
You want me to go like this?
Yeah.
Is that prettier? I think it is a little prettier, actually. Yeah. Normally, I'm a big whiteboard person, so I like whiteboarding things out, but I want this lecture to be accessible to people who are watching online, so that's why I'm doing it in a notepad document. But yeah.
So
Mm-hmm.
EDRs usually block malwares which are signature based, right?
So
Let's
I
say
feel like I have a slide on this from the original presentation, but it's a good point to mention. Anyway, so the difference between antivirus and EDR, and now it's more of a blend. Back in the day, there was this was a more clear difference, but now antivirus kind of have to evolve to become more EDR-esque. Anyway, point is, an antivirus does this static analysis and dynamic analysis, right? So it looks at those it looks at those files on disk, or it looks at maybe running memory and sees if there's known malicious code, right? Basically, or known malicious bytes. Dynamic analysis takes a file and runs it in a sandboxed environment. Sandbox meaning contained, so that the malware can't actually do anything bad, but the antivirus can observe what it is doing, right? And then it can say, oh, it's taking these actions, it's probably malicious. Dynamic analysis only works with files that are on disk, because fundamentally what it does is it takes files on disk and it runs them. EDR adds a third element to that called behavioral analysis. And EDR, we're actually going to kind of get into how this works a little bit more in a second. But EDR also looks at the process while it's running. It looks at things like, okay, so what DLLs or libraries did that process load? What network connections is that process making? What files is that process changing, right? And it looks at that while the process is running. So that's what an EDR does. An EDR does this static and dynamic analysis also, but it has that third element of behavioral analysis on top of it.
So then, meaning those solutions could use some of these functionalities, AMSI, ETW, Kernel.
Yes. So that excellent point. A lot of EDR make use of AMSI. They make use of ETW, and they combine that with their own methods to then detect what's going on. But yes, absolutely. EDR does make use of AMSI and ETW. Which reminds me, I should also add DLL hooking.
Can you just put the full meaning of the ETW and the AMSI there?
Yeah, sure. Anti-malware scan. Is it scanning or scan? I think it's just scan.
Yeah, it's not.
How about that?
Mm-hmm. Yeah.
Okay, do we now understand like how AMSI works?
Yes.
Cool. The next thing that actually I'll talk about the things that are more built into Windows as opposed to the optional things. We'll talk about the optional things later. So, actually, why don't I say that? Built into Windows. And optional. And another thing I'm going to do is I'm going to pull up Yes, I make a lot of PowerPoints in different places. Okay, we're going to get there. The next thing that I'm going to talk about is event tracing for Windows, or ETW. ETW, when it was created, it actually wasn't intended to be used for defense. ETW is just basically a massive logging framework. You can think of it like that. Maybe somebody who knows Windows internals very well will get mad at me for calling it that, but I think that's the easiest way to think about it, right? Now, ETW gives you a lot of that data, that behavioral analysis that an EDR would. It can tell you like what DLLs get loaded. It can tell you what processes are spawned. It can tell you what network connections are being made. It actually uses a variety of different methods for doing that, both on the user level and both in user land and in kernel land, and provides you a lot of insight into both the legitimate things that are happening, and you can use it to potentially detect malicious actions, right? ETW wasn't originally intended for defense, right? It's intended to give you a better view into what's going on in your system. But of course, that's really useful for defenders, because when you have that view, then you can make alerts or make rules off of specific things that happen. Does that make sense? Okay. You're actually going to get really familiar with ETW, and the reason I say that is because I added Aurora EDR to the environment. I think last week I said, or 2 weeks ago, whenever we met, I said that there's no good free EDR for Windows. I was a liar. I was actually working with Splunk's attack range GitHub, and it used Aurora EDR, and Aurora has a free light version. And what Aurora does is it only takes ETW and it makes rules based off of information that it collected from ETW, right? So Aurora is an ETW only EDR. It basically takes all of that ETW log data, because that's what ETW is. It's just a bunch of data that we can make use of, and it puts rules on that. It actually uses a way of writing rules that's called Sigma, but it puts rules on top of that, and then we can detect on certain actions. And as we're going through the lab, you'll see just how useful that information that we're getting from ETW can be. But just like with AMSI, ETW can be bypassed by attackers. Because it has a user land component to it, if you were to patch the function, one of the functions that makes it work fundamentally, then it will no longer be effective. Anyone want clarification on ETW or how Aurora uses that?
So ETW works similar to one of the sysinternal tools. So you said it has a dashboard where we can see things like a defender, right?
No. So ETW is just a bunch of logs in a way, you can think of it, right? It doesn't have a dashboard or anything pretty. It's just a bunch of data. Aurora EDR, which we'll be using, uses ETW, and it has its own dashboard that then you can see alerts in.
What kind of alerts?
Whatever you want to create. You define what you consider a malicious action. You create a rule for that, and then you can set an alert level for it.
Okay.
And when I say alert, I just mean something that shows up in the dashboard that then you know that you should respond to it.
So the ETW only works with EDM, Aurora EDR, correct? Not the AMSI.
Yes, so AMSI and ETW are two separate things. They're both used. A lot of the times more advanced EDR will make use of both of them, but they are two separate ideas in Windows that are just both useful for us.
So, Aurora is an example of ETW.
So
It uses it.
Aurora is just an EDR. It's a specific solution that somebody developed, right? And it relies on ETW for its data, right? It takes data in from ETW, and that's what it works with.
Yeah.
But it's not native to Windows. I know I kind of put it here, which is a little misleading because I put it under the built into Windows section, but I just wanted to show you that the Aurora EDR, which we will be using, relies on ETW. But ETW is that logging mechanism that's built into Windows.
Okay,
Yeah.
so can Aurora also make use of Linux?
System logs.
Yes.
I mean, an EDR could, but Aurora specifically does not. That's just how it was designed. It was designed just to use ETW.
Is it open source?
It is, I think it's open source. I'm pretty sure it is.
And the leaders in this EDR business is Sentinel and CrowdStrike.
Sorry, say that again?
The
Falcon.
leaders in this
CrowdStrike Falcon.
EDR business is Sentinel and CrowdStrike.
Yeah, I would say so. Cortex, Sentinel-1, CrowdStrike, Carbon Black. I'm sure there are others, but those are probably the biggest. The biggest one I see is CrowdStrike,
Yeah.
I would say.
CrowdStrike Falcon.
Yeah, it looks like Aurora's open source.
Okay.
But as you can see, it takes data from ETW, it applies rules to it, and then you can choose what you want to do with that, right? You can log it to a file, you can use it to create responses, automatic responses. But fundamentally, it's just built on top of ETW. Cool.
So where do application like the registry editor come in? Does it use any of those?
So no. So the registry is, I guess, you can think of it as a special set of files in a way that you can use to configure your Windows machine, right? It's actually stored on disk in a couple different locations, depending what registry hive. It's organized into these folders called hives. And those hives are located in various places on disk, depending which hive you're looking at. But those are basically, you can think of them as configuration options for Windows. They don't have anything to do, well, they might influence certain things. Like, yes, there is, I believe, a registry key to influence ETW or a registry key to influence script block logging, right? Because fundamentally, it's just a configuration, a massive set of configuration files, right? But they're not actually logs, right? They're configurations.
So this picture you have, this Sigma config, agent config, what are those? I know the rules. What the Sigma config and the agent config, that's the configurations you set for the Aurora?
Yeah. So I'll get into Aurora later on, but Aurora does have its own it has its own configuration file that defines how Aurora behaves. And then for the rules that it's using, which are called Sigma because they're in the Sigma format, right? Another open source rule writing format. And it has its own configuration for defining Sigma rules. Yeah. I'm actually going to put this, I'm going to delete this for now so you don't get confused, and I'll put it in a different section, but ready to talk about also, somebody mentioned, I think you mentioned sysinternals tools, and you talked about how they're similar to ETW. Well, actually, a lot of sysinternals tools use ETW, and that's where they get their data from. So Process Explorer is an example of a sysinternals tool that uses ETW to show you like what DLLs are loaded, or there's certain information in Process Explorer that it uses ETW for. And we can actually show that if we and I might actually show this next week, if we bypass ETW for a specific process, sysinternals won't be able to actually get data, Process Explorer won't be able to get the data for that process. I always forget if it's Process Explorer, Process Monitor, but I think it is Process Explorer. Anyway. So the third kind of built into Windows place where we can get useful information is something called kernel callbacks. So whenever you're trying to do something that requires you to interact with the operating system, like when you connect to, when you do a network connection or when you write to a file, you need to be able to tell the operating system to do that, right? And so this will make more sense too when I show the process for getting into the kernel. So just bear with me. But everything that requires OS interaction goes to this kernel land, right? So we'll have a function in the user land that we can run, and then that will jump us to the kernel land. When I say kernel land, I basically mean the space that the process itself has no control over, because the operating system is in control. Like the process stops being in control and the operating system starts being in control. The way computers fundamentally work is they're running a bunch of processes simultaneously, right? When we say simultaneously, the computer science-y term for that is concurrently.
Yeah.
Why do we say concurrently? Because your computer can't run multiple things at once. It actually switches back and forth between things really quickly, but it does it so fast that you as the user don't feel like it's switching. You just feel like they're running at the same time. Does that make sense?
Yeah.
The operating system or the kernel is responsible for switching between processes.
Okay.
Right? So you, as the program developer, you have control over what your process does. So you have a specific set of code that you wrote for your process, and it runs through that code. And that's all you know as the developer. However, the kernel is running your process as well as like hundreds of other processes. And it's actually has to do all the tasks like switching back and forth between them. Does that make sense?
Yes.
So your program does not have control over the kernel. Your program only has control over user land. Or user land is basically saying anything that your program does. And kernel land is saying anything that the operating system does that you don't have control over.
Okay.
So far, so good?
Any kernel land is anything the user doesn't have control over.
Right. You can think of it that way. Kernel land is anything that the operating system is doing that you don't have control over.
Okay. Switching processes.
Yes. And user land is anything that you wrote in your code that you have control over. So far, so good?
Yeah.
Okay. But, so let's say you have a button, like this button right here, that's supposed to open a file explorer, right? So when I click this button, it opens this application, right? That opening that application creates a new process, correct? So we need a way from one program to be able to open another program, basically, right? Because that's fundamentally something you would want to do. However, like we talked about, it's the kernel that's in charge of everything that's going on under the hood, like all the processes that are being created. You're not in charge of that. It's the kernel that's in charge of that, right? So you need a way for your program to talk to the kernel and say, hey, can you create this new process for me? And then the kernel will take that message and be like, okay, and then it'll do its own thing. It'll create the process, right? Mm-hmm. So the kernel is in charge of creating the process, but your program has to have a way of telling the kernel, hey, I want to create a new process. Does that make sense? Yeah. Cool. So this, and creating a new process is one example, but there are many things that we need to interact with the kernel for. So making network connections, right? How Windows actually makes network connections is handled by the operating system, by the kernel. But a web browser has to be able to make network connections too, right? And it does that by reaching out to the kernel and saying, hey, can you make this network connection for me and give me the response? The program tells the operating system, hey, I want to reach out to google.com. Well, I guess it's more granular than that, but we can pretend for simplicity's sake. The program tells the kernel, or it tells the operating system, it says, hey, I want to reach out to google.com, give me the response, right? And then the kernel actually reaches out to google.com and gives the program back the response, right? And how it actually does that is handled, under the hood by the operating system. The only thing the program needs to do is call this specific function that tells the kernel to reach out and give it back the data. Does that make sense?
So the kernel is the one that makes the network connection to Google.
Yeah.
And then brings back the response to the application.
Yes.
The user gets it.
Exactly. So the program just says, this is what I want to do, and the kernel handles all the behind the scenes and actually does it. Does that make sense?
Yeah.
Cool. So how do we actually do that? How do we tell the kernel what to do? We use a special kind of instruction called a syscall instruction. So when you write your program in like C or C++ or Python, and it gets either interpreted or compiled, but in the end, it's just machine code, right? And machine code is just instructions like move this to this, add this to this, right? Mm-hmm. So there's a special instruction called a syscall instruction that is used to jump, or when I say jump to the kernel, I mean to tell the kernel to do something for you, right? And these syscalls have different numbers that like correspond to what you actually want to do. So let's say you want to create a new process, you would run the syscall instruction and you would give it the specific number that's associated with creating a process. And then the kernel would know from there, okay, we're going to stop this process from running. We're going to take that instruction. We're going to do what we need to do with it. And then we're going to return to the process. basically, that was a lot of words to say this syscall instruction is a specific instruction that you can include in your code to tell the kernel to do something for you. Does that make sense?
So it's like the different languages all reach out to the system.
So different languages need to be first converted to machine code, right? Before you actually run an application. Once a developer develops an application, they then compile their code, if it's a compiled language, like C++, for example. Or like Python is kind of a special case. It's an interpreted language, so it gets converted to this intermediary language. In the end, it all gets converted to instructions, right? And then when you're actually running the code, you're running these instructions, right? So the developer created the code. Let's say they compiled it. Now it's just a bunch of instructions. They pass it to the user as a bunch of instructions in a file, like, for example, a .exe file, right? And then the user, or whoever's going to be using the application, double clicks to run the application. And that application is just a bunch of instructions at that point. And so one of those instructions can be a syscall instruction that tells it to jump to the kernel, or tells it, I keep saying jump to because that's like the formal word for it, but that tells it to get the kernel to do something for it.
Maybe like create a variable.
Yeah.
Create a variable.
So actually that's maybe not the best example, because variables you can create, you have control over a piece of memory. Your application has control over a piece of memory. And so you can add data to that memory without having to talk to the kernel. But for certain things like spawning a process, that's where you would use the syscall instruction to talk to the kernel. Programs themselves usually don't include the syscall instruction. Instead, what they do is they load in libraries. So this syscall is just a low-level machine instruction, right? That would be kind of annoying to use for developers, because like when you're developing code, you're not writing out machine instructions, right? You are calling functions, right? So then what Windows has this special DLL. DLL is just a library, right? So you can think of when you do import in Python or include in C, right? Basically, a DLL is just a file that has these libraries in it. In this specific NTDLL, right, the special DLL, it has functions that you can use to then have a syscall inside them. So like, let's say you want to create a new process. You could either run syscall and then a number that indicates that you want to create a new process, right? Or in NTDLL, there'll be a function called ntcreate, I'm forgetting now, ntcreate process X or something like that, or ntcreate new process. And that function inside of it will have a syscall. And as a developer, it's much easier, instead of running the syscall directly, to just call that function. And then that function, because it has a syscall inside of it, that will cause it to jump to the kernel. Make sense?
So would you say a DLL is like more like a container containing a number of syscalls?
Yeah, in a way, it can be looked at that. It can be looked at it that way. Yeah, a DLL is just a bunch of functions that you can make use of in your program.
So I'm referring to the NTDLL.
Yes, NTDLL specifically is like the one big one that, you're right, is used to jump to the kernel. Like, it has all the functions you would need to jump to the kernel. In NTDLL, you have your most basic building blocks, like spawning a process, creating a thread, doing things like that. But for more complex things, you might want to do a combo of those, right? So when you spin up a process, you probably want to spin up the process, unsuspend that process, create a thread in that process, and actually start the application, right? That's a series of steps, right? And while NTDLL is going to have the building blocks that you need for that, so it'll have a function for starting a process, it'll have a function for changing its state to running, it'll have a function for saying this is what code I want to run in that process, right? That's also still pretty complicated for developers to like call all of those functions to do something like this. So we need another layer another set of functions, basically, that just call those lower level functions. So a function is just a group of instructions, right? So you can take all of those NTDLL functions, you can put them together and create a function to make life easier, right? And that's where we have these higher level DLLs, like kernel32.dll is one example. There's user32.dll. There are these DLLs in Windows that basically just make the functions in NTDLL easier to use. Does that make sense? So all of this was to say, if you have an application and you want that application to spawn a new process, let's say, what you're going to have to do is you're going to have to call, let's just use thread as an example since I have it written out here. Let's say you want to create a new thread in your current process. I'm not going to really get into like processes versus threads versus all that. But let's say you want to create a new thread in your current process. The point is you would run create remote thread in kernel32.dll. So you would include kernel32.dll. You would load that file. There's a kernel32.dll file on disk that has all those functions. You would load that file into memory, right? So you have all those functions. Then you would call that create remote thread function in kernel32.dll. That create remote thread function will then call the corresponding functions in NTDLL, right? Like, for example, nt create thread x, which is much harder to use, but it's as low level of a building block as you can get, right? And then that function in NTDLL will run the syscall instruction that jumps you to the kernel. The kernel will do its thing and it'll give you back a response, right? And this is the normal process flow in Windows and Linux. Of course, in Linux, we don't have kernel32.dll and NTDLL. We have, I believe they're .so files or but also library files, basically, that the process would import that would have a similar setup to this. Questions so far? We actually talked about what I would consider a really advanced malware development concept. So the fact that you guys got this, great job. But why was all this important? Now that we know this, we can talk about some of the things that I was trying to talk about before, but you had no context. So it was kind of hard to talk about it. The first one was kernel callbacks, right? So I talked about how whenever you jump to the kernel, there's a certain set of things that get run when you jump to the kernel. So whenever we run any syscall instruction, so whenever a program calls this, which jumps us to the kernel, in the kernel level here, we can actually grab that syscall instruction that it ran and we could log it or we could take note of it, right? So an EDR could be like, oh, look, somebody called the syscall for creating a new thread, right? And it could log, okay, this person created a new thread. And that's a kernel callback. The way it actually works is for specific syscalls. So there's a certain set of syscalls that have a list associated with them. And that list is a list of things that happen when that syscall gets called, basically, right? And an EDR can add to that list. They can say, I want to be part of this list so that when you use the syscall instruction for creating a new process, it's going to notify me. Does that make sense? That's kernel callbacks. Cool. Wow, I'm teaching malware development, guys. All right.
It looks like it makes sense to create signatures based off processes because the malware can call specific processes. So if they can be known, that means it can be written down by and then given out to register the processes that malware run, right? Because the malware will always run the same kind of process. So that means it makes sense to create a signature based.
Yes. Processes may not be the best example, although I guess it's a fair example. Let's say you have you have a fake or malicious Microsoft Word document, right? And that Word document, when the user opens it and clicks enable content, it actually spawns a PowerShell process and runs something malicious, right? It's going to be very unusual for Microsoft Word or the winword.exe process to spawn PowerShell or to create a PowerShell process, right? So exactly, if you had a kernel callback that looks at process creation, right? Like your EDR was looking at that, then it could be like, that's weird. I can see winword.exe just spawned PowerShell. And even if an attacker disables things like ETW or AMSI, those live in the user space, right? So they could disable those, but they can't disable kernel callbacks because they don't have access to the kernel.
Is it similar to the executable you were trying to do in CCDC? Like whenever you're trying to open up a PowerShell, it is spawning the PNG file. So you attached in a similar way.
How do I explain this? I created a backdoor that whenever you start PowerShell, it actually opens a different program, right? It actually does not use kernel callbacks. It doesn't. You could monitor that with kernel callbacks. Like you could see that one process is spawning another with kernel callbacks. And I think if you wrote a driver, you could actually do it with kernel callbacks too. Like that is a way that you could do it. That just did not happen to be the way that I did it, right? But yes, that concept, you could basically do anything. Like you could say every time the syscall instruction is called, I want to do this instead. Like I'm going to hijack execution. Yeah, absolutely. And also, just so you know, whenever you're writing code that's going to be used by the kernel or to modify how the kernel works, you're creating a driver, not a program. So that's the difference between a program and a driver. So most of the development that you're being taught in the CS class is how to create a program that works in user space. But you can take a lot of those same concepts and use like C or C++ to write a kernel driver. And that driver you'd have to load into the operating system, and then you can modify how the actual operating system works. So yeah, a lot of these EDRs, they'll actually have their own kernel drivers that'll do things like kernel callbacks.
Yeah, on that note, so when you say the attacker has no access to kernel, does that mean they cannot modify what the kernel does, or they cannot like completely shut down our kernel for the laptop to go down?
You must be a very good developer to do that.
They cannot modify what the kernel does. That is correct. Unless they are able to load their own malicious driver. Which, like, if you're a local admin on a machine and let's say you Microsoft sign, because I think Microsoft requires Microsoft sign drivers by default unless you disable that. But if you Microsoft sign your driver, and an attacker could load their own malicious driver to then take control over the kernel. But there are other ways to brick a machine and make it unusable than having to interact with the kernel at all. As a local admin, you have full control over your machine, even through syscalls, right? So you don't need to have kernel level access to do privileged actions. Make sense? Woo! Actually did not expect to spend so much time talking about this, but this is great. I'm loving this. All right. The other thing that I'm going to talk about first, now that we talked about this whole user land, kernel land thing, is DLL hooking. So like we talked about, every application relies on these DLLs, relies on these functions, right, that eventually call a syscall. It is not customary for an application to run the syscall instruction. Usually they call a function in kernel 32 that calls a function in NTDLL that then has a syscall instruction, right? So far, so good? So, what
are these DLLs? What are DLLs?
DLLs are files that contain a bunch of functions that you can make use of.
Okay, they are .dlls.
Yes, so there are actual files on your machine there is a file called ntdll.dll, right? And then every time a process is created, if it wants to use any of the functions in NTDLL, it has to take that file and load it into memory.
Yeah.
And then it has those functions and it can make use of them. That's what a DLL is. It's just a library file. So,
Yeah, one quick
yes,
thing.
go
So,
for it.
the program.exe and ntstr.exe, those two have different extensions, and I thought like the first extension is at the application level. So why is it that we have two like .exe extensions?
So why do we have .exe and .dll?
No, .exe and the
Up
last
and
one.
down in the
Up and
kernel
down.
station.
So I thought in the kernel
Oh.
we should not have like .exe there.
Yes, there is actually a special process in Windows, or a special file in Windows that has all the code for the operating system. And that file is ntoskrnl.exe. That file is fundamentally, when you boot up your Windows machine, that's what gets run. That's a little bit of an oversimplification. Again, there's like a whole series of things that like all spawn each other and get run. But fundamentally, in the end, NTOS kernel is the
The file that contains all the code that runs the system.
yeah. So okay, let's talk about the limitations of kernel callbacks. Their kernel callbacks are only applicable to specific syscall instructions. It's not like there's a kernel callback for every single syscall instruction. So with syscall instructions, you can see some things, like you can see there are some things have kernel callbacks, like creating new processes or loading in DLL files. So you're going to see all that. But you won't see, I believe there are some syscall instructions that don't have kernel callbacks associated with them, so you can't actually like hijack the execution flow there. And anything that doesn't require syscall instruction, you're not going to be able to see, right? So you're very limited. If you only rely on kernel callbacks, you have a very limited view of what a program is actually doing, right? You can see what libraries it's loading, you can see what processes it's spawning, but you can't see. I don't have like good examples off the top of my head, but you're limited in the kinds of things that you can see. Does that make sense? Let's say we want to get more granular and see everything that a program is doing. How do we do that? Well, we know that every program is going to call these functions in kernel32.dll. So what we can do as an EDR is whenever a new process gets created and it loads that copy of kernel32.dll, we can jump in there and we can overwrite some of the functions in kernel32.dll so that they actually jump over to our EDR. I know it's kind of like, because fundamentally, everything in kernel32.dll is just a bunch of functions, right? It's just a bunch of low-level code. So if it gets loaded into memory, and then the EDR goes in and loads itself into memory and overwrites those functions, it could basically have those functions do whatever it wants them to do. So a lot of the times, EDR will overwrite the first few instructions of that function with a jump instruction that tells the program to actually jump to the EDR. And then the EDR can log that function was used, and then it would jump it back to the rest of the function. I know that's very like fancy, complex, but that's what they do. And that gives you great visibility as an EDR because now you know every function that the user ran, assuming they're using kernel32.dll. So that is DLL not DLL hijacking. What is it called? DLL hooking. Sorry, I'm blanking here. So that is DLL hooking. It's called hooking because those instructions that you add to tell it to jump to the EDR is called a hook, right? So now let's think about this. So let's say an EDR will often hook multiple DLL files, right? So let's say it hooks kernel32.dll. And what does hooks mean? Basically means it overwrote the first couple instructions of every function so that it jumps to the EDR and runs EDR code. So in practice, a program wants to create a new thread. It runs create remote thread in kernel32.dll, right? That's the function that it calls in the program. But remember that function was overwritten. The beginning of that function was overwritten so that we jump to the EDR.
Okay.
So then we go over to the EDR. The EDR takes some sort of action. And then from there, the EDR can run the rest of that function, right? Which will take us then to NTDLL.
does the EDR monitor all everything, or it will monitor specific?
So when we jump to the EDR is hooking everything in kernel 32.dll. So let's say every application that's using kernel 32.dll has these functions that are hooked, and they jump us to the EDR. The EDR can choose to like log that we used create remote thread, or it can choose to do nothing. And in many cases, it'll just choose to do nothing, and it'll jump us back and let the program continue executing, right? And from the perspective of an end user, you don't notice, there's no noticeable difference because these instructions execute so fast, right? That just one jump back and forth doesn't make a difference.
Meaning the rule was that kernel 32.dll. That's where the rule for the EDR was.
Well, so the EDR is hooking the function. Yeah, so every time a program loads in kernel 32.dll, let's say the EDR is going to hook the functions in kernel 32.dll. But attackers were like, okay, well, if you're going to be hooking kernel 32.dll, why don't we just use ntdll? This is kind of the code for doing it, but this is the diagram explaining it. Why don't we, instead of using kernel 32.dll, we'll directly call the functions in ntdll. If we directly call the functions in ntdll, it doesn't matter if you have hooks here because we bypass them by calling the functions in ntdll, right? So then defense solutions are like, okay, well, then if you're going to call the functions directly in ntdll, why don't we hook the functions directly in ntdll? So now if you try to call those functions, those are hooked too. So then attackers are like, well, wait, why do we even have to use those functions in the first place? Why don't we just use syscalls ourselves? Like, why don't we call the syscall instruction and jump straight to the kernel?
That will have so many false positives.
Yeah.
If you put the EDR at the syscall, that's so many false positives.
Well, yes, but the EDR can choose when to take an action or when to just jump right back. We're just saying we jump to the EDR, and we can log it, yes, but we don't have to. Like, the EDR will decide whether this is interesting enough to be logged or not to be logged, right? So for certain functions, it could be like, okay, well, we'll log it. If we previously saw that you ran create process X to create a new process, and now maybe we logged that, and now we see you're running create remote thread X, maybe we want to log that because you previously ran create process X, right? And that's a known combo that an attacker would use to like create a new process and inject code into the process. I know that was a very technical example, but yes. Anyway, so then attackers were like, okay, why don't we use syscall instructions to jump straight to the kernel? Okay, so that's DLL hooking. So these are all different like defense measures that are going to come into play. The next thing is PowerShell script block logging.
Question.
Yes.
So does unhooking the DL disables the EDR?
In a way, well, it doesn't actually stop the EDR from running, but for that current process, yes, it disables the visibility that the EDR has into that current process. Maybe not fully, because if it's using kernel callbacks, there's still things it can see. But yeah, if you unhook DLLs, which we will do, maybe not next week now, maybe it'll be the week after, but whenever we run the attacks, you'll see when we unhook DLLs, you're going to see a lot less as a defender. But there are still other... defense is like a combination of all of these things being put together, right? So you'll still have the other ones that you can maybe rely on.
So what if the attacker overrides our DLL instructions or those instructions and they're overrated?
That's exactly what unhooking is. Yes.
So are there applications that, if you update the system, does it re-update? The attacker has already overwritten our normal functions, right? So we want to like, maybe if you run the scan, can it re-update the function?
I know what you're saying. Like, what if an attacker actually overwrites those functions to do something malicious, right?
Do we update the system? Does it fix the problem if we update the system?
I'm going to say probably not, because when you're downloading an update, you're not re-downloading all the files on the system. You are downloading additions to the system, right? And that's why it's so hard to get attackers out. Like once they're in, if they do something really advanced like that, they're like, it's going to be really hard to find that for sure. So then you have to rely on the logs that you had previously collected to figure out what they did. So maybe you'll see that they interacted with the NTDLL file on disk, which is unusual for anybody to interact with the NTDLL file on disk. So then you'll be like, that's weird. Like, and then you might go in and you might see that it's no longer a clean copy of NTDLL. And also, well, so if we're talking about that, binaries like NTDLL, all of these Microsoft things are signed by Microsoft. What does signed mean? Basically, it uses public key cryptography to prove that that file is intact. So if an attacker were to modify it, the signature on the file would be broken. The way it actually does that is public key cryptography. So Microsoft has a public key and a private key, right? So they would take the file, they would maybe hash the file to make it like a hash is a smaller version of the file that's going to be unique. When you change things about the file, the hash will change, right? And then they will use their private key to sign the hash, right? And that'll be embedded into the file. And then when you're looking at the file, if you can, the public key is public. If you can decrypt now I'm kind of explaining public key cryptography here, but if you decrypt that hash with the public key, then you know that it was signed by Microsoft or signed by somebody who has the private key. And that private key is owned by Microsoft. And if an attacker makes changes to the file, then if you tried to compute a hash of it, it wouldn't actually match.
The hash will change.
Yeah. So that's because binaries are signed by Microsoft, you know when an attacker's changed it.
And also,
not to mention you're probably logging interaction with system files would be kind of an important thing to pay attention to.
And also in this internal source, when you try to verify the signatures, it will say unverified.
Yes. So if you're using, for example, autoruns, autoruns is an example of a sysinternals tool that will look for things. It looks for a lot of things like scheduled tasks, registry entries. But yes, it will point out when files or when some of those things are not signed by Microsoft, have been modified. So if you have a custom, I believe Process Explorer does it too. If you have a custom process that's like not actually a Microsoft program, like it'll display it in a different color because it's not actually signed by Microsoft.
What if they do indirect syscalls, like not go through they can call through a trusted process, right?
So you're saying, let's say we inject code into Explorer, or we run Explorer, we inject code into there and use Explorer to do things. Yes, that isn't a technique that an attacker does.
Malicious.
Absolutely. Great thinking. And that is an attack technique. It's called process injection. Yep. That's when you either create a new process or because processes have, to some degree, they can interact with each other. They have to be able to. Like when let's say you want an application that opens, this is maybe a bad example, but let's say your application is supposed to open a cat picture, right? Maybe you have to not only start that process, start your Photos application, but you also have to tell it what file to open. So maybe you have to tell it some code to run, right? So that's necessary. But then an attacker could also inject code. They could take code and they could inject it into an already running process. They actually do that by interacting with the kernel, right? Their create remote thread or NT create remote thread X is like the NTDLL function that they would use to do that. And yes, that is something attackers do to mask their behavior.
We cannot do anything. Can we do anything about it?
Well, first of all, ETW and if you're using kernel callbacks, you can see when one process injects code into another process, right? So you can see when that's happening. And if it's like a weird injection, like you wouldn't expect PowerShell to inject code into your web browser, then it can alert on that, right? Or block that from happening.
What do you do to become extremely good at defending?
What do you do to become good at defending?
Attend these sessions.
Yes, you attend these purple team sessions where you learn this stuff. No.
I think there's a lot of stuff for that.
Ideally,
We also think like in order to beat attackers.
Yes, that is exactly what I was going to get to. To be a good defender, you should understand fundamentally how your machine works, right? That's step one. If you understand how your machine works, you can start thinking about ways to abuse that. And when you start thinking about ways to abuse that, now you know what the attackers are doing. And knowing what the attackers are doing, now you can start thinking about ways to prevent that. So I think fundamentally know how things work. The more you know, the better. You're never going to know it all. Then know how attackers abuse how things work, or think critically, like how would you abuse it? And then from there, think about how would you stop it from being abused that way? And how can you use these different sources of telemetry or different sources of data to catch attackers who are abusing things like this? Yes. All right, great question. Any more questions before I move to script block logging? This is going to be the most like, we went so low level, now we're going to go back to a high level. Script block logging, very straightforward. You can choose to log every command that gets run in PowerShell. And that's called script block logging, right? That's something that is not enabled in Windows by default. But you can enable it, I think, in the registry. I'm now blanking, but yes. I think in the registry, you can choose to enable PowerShell script block logging, and then it'll actually log every command that gets run in PowerShell. Again, that happens on the user land, because it actually checks like what commands that process is using. So attackers can, of course, bypass script block logging in the same way that they can bypass AMSI, ETW, or anything that happens in the user land. But it's just another source of telemetry for us as defenders.
Yeah, in Linux, every action gets translated to command line at some point. Is it the same thing with Windows as well?
Yeah, pretty much. All code gets converted to machine instructions. So, I mean, it doesn't necessarily get converted to a command per se. It gets converted to machine instructions. And commands are also just easy ways of like running groups of machine instructions. And it works the same way in Linux and in Windows. Yeah. Okay, do we kind of now understand like these are all the different places where we can get data from in Windows? And okay, so talking about what do organizations actually do in the real world? Organizations will be like, okay, we're going to use CrowdStrike, and then we're going to maybe like use Splunk with its default forwarders, right? And they're actually missing, like, for example, PowerShell script block logging, or they're missing Sysmon, or yes, CrowdStrike is leveraging ETW, but they're missing like directly looking at ETW, right? And that's where we have holes in detections, because they expect, and I know I'm saying CrowdStrike, not just CrowdStrike, they expect their EDR to catch everything, and their EDRs don't catch everything. And you have to fine tune EDRs to get them to catch the things that you want them to catch, because out of the box, they're meant for the average company, not for your company, right? And your company might have a different baseline of what's normal for your users to do. Anyway, just wanted to make that point. Another point to make is EDR, the way we're doing it here, EDR is going to be fed into your SIM. So remember, SIM is just this place where we aggregate logs and we can alert on them, right? So it's really straightforward, or it's really nice to have our EDR logs also being forwarded to the SIM. So we have one platform that shows us everything. A lot of organizations don't do that. They have a separate dashboard in the EDR and a separate dashboard in the SIM, and they just look at both. So I just wanted to make that point. Like, we did have this whole talk about, now I have to go to my other PowerPoint, which I don't really feel like doing. But we had this whole talk about like EDR logs get forwarded to the SIM. That's a choice. I think like in a most mature environment, you want maximum visibility and everything gets forwarded to one place. But depending on your environment setup, you may choose not to do that. Or if you have like different teams that handle different events, or if maybe that's too much data to send from one to the other, and maybe it makes more sense to use the two separate softwares. So I just wanted to make that point that the way that I'm showing you how to do it here is like quote unquote the ideal way, but it's not always doable for every organization. Okay, now, so this is kind of the data that we have, and then how do we make use of this data? At least in our environment, this is how we're going to make use of this telemetry. I will start saying telemetry so that you get used to that verbiage. So we're using Aurora EDR, and Aurora EDR takes in ETW, right? Aurora EDR is built on ETW. It reads those ETW logs and has different rules based on that. Then the other thing we're going to use is Sysmon. Sysmon, like we talked about before, is an extension to Windows that gives you more visibility into what's happening, and it uses a combination of different things. So I believe it uses kernel callbacks. It also it does a variety of things that we have here to give us like more visibility into like process creation and certain things, right? Any questions thus far? Okay. So let's talk a little bit about how I set up and this is in the resources section. I showed this to you last week, so this should look somewhat familiar to you. But the one thing I added to it, so you'll see here we have this was a Windows role in Ansible. Ansible, again, is an automation framework that I could use to install things on multiple machines at once without having to manually go to each one. So I actually wrote a bunch of tasks in Ansible to install this stuff rather than installing it all by hand on all like whatever 6 Windows machines we have. But this was a Windows role. It just installs the Waza agent, right? And the Waza agent is what forwards logs from the machine to Waza. Then we have Sysmon. Like we talked about, Sysmon uses a variety of different types of telemetry to give us more insight into what's happening, like process creation, registry modification, that kind of stuff. The way you install Sysmon is on Microsoft's website. They have this binary that you can download, or this executable file that you can download, and then you specify your Sysmon configuration. You have to like kind of configure it to determine what events you want to collect or what information you want to collect. And then you run that executable file and you provide it the configuration. The configuration I used is this really popular Swift on Security Sysmon configuration that's open source and just has like a lot of default. It has like, it's intended for being used in most environments, right? It has different rules for Windows normal Windows processes to exclude. Basically, it's just a configuration file that somebody else put together for me, so I don't have to put one together myself.
I was just going to ask about those process exclusions. It's like that's a lot of XML to.
Yeah. So, yeah, a lot of times in organizations, not every organization is going to be able to go in and write all of that themselves. So then they're going to have to rely on some publicly available one or maybe one that they bought from somebody. But yeah, to exclude all of the normal Windows processes, right? Because otherwise we'll be just getting way too much data. Yeah. So, but anyway, I use this one. And this is a very popular one. Then we have, Windows Defender, when it actually alerts on something. So Windows Defender is fundamentally an antivirus, right? So it will look at files on disk and it will do static and dynamic analysis like we talked about before and see if it finds anything that's malicious. By default, that data does not get sent to Waza, right? We have to actually say that we want to send that data from Windows Defender to Waza. Windows Defender actually logs everything that happens. So like when it detects a malicious file, it writes that into our event logs. In Windows, everything gets logged to this location called the event logs. And so this role in Ansible just tells it, hey, take those logs from Windows Defender and also forward that to Wazza, right? Then we have PowerShell logging. So this both enables PowerShell logging, I think, in the registry, and we are about to find out. And since it's Ansible, I feel like it's pretty easy to read. Like you can kind of tell what's going on here. So look, we have a registry regedit, modify the registry. Here's the registry path. Here's the name of the key we want to modify. Here's what we set it to, right? So here we're enabling script block logging. And then just like with the other ones, we have to add, we have to make sure that that script block logging gets forwarded to Wazza, right? We talked about this last time too, which is why I'm not going over it, but to forward things to Wazza, we define that in Wazza's .conf file. So whenever we want to forward a specific log source to Wazza, like a file or Windows events, right, we have to add these lines to this ossec.conf file in order to do that. I know we kind of talked about that last time, so that's why I'm brushing over it. And then the last thing that I added is Aurora EDR. So like I talked about, Aurora is an EDR based off of event tracing for Windows, or uses event tracing for Windows. You do have to create an account with them and download a license, but it's free, so you can create the account for free. So I created a free account, I downloaded a license, this installs Aurora EDR, and then I have this license file here that it just copied over from the machine that I ran Ansible from to all the machines so that they're properly licensed. Make sense?
Yes.
If we take a look at what Aurora actually looks like. Also, this server 1 is the machine that I'm going to be using to demo a lot of the checks that we're going to run. So this will be my demo machine. I don't think you have access to it over the VPN yet, but I will make sure that you have access to it when it comes to actually running the attacks and stuff. Anyway. Going on here, you'll notice now that I installed Sigma, we have this new icon here, which is the Sigma dashboard, right? If I click on it, it actually brings me to this nice dashboard where I can see all the different alerts that it's giving me, right? And you can see how granular it gets. Like, look, I opened Notepad and it's alerting that Notepad plugins was in the target file name, right? You can see how granular it gets. Also, how do we actually configure Aurora? So Aurora is installed similar to Sysmon, where they give you this executable file. You run it and you tell it what configuration you want to use, right? And then it installs it from there. But in the end, if we go to C program files, Aurora agent, these are all the files related to Aurora. So the main configuration files, the main configuration file is here in agent config. So this is our general options that we can change, right? Including where we want to log things to. So everything that Aurora finds, we can log it to a log file, which is what we're doing here. Our rules are defined in, if I can remember, not response sets, in signatures, Sigma rules public, right? So each of these, so here we have a bunch of different folders that each contain different rules that it's using to log or alert off of. And these are the default rules that came with it. Like, I did not change anything here. You could, of course, go in and you can change these to your liking. They're in like a nice, easy to modify Sigma format. But I'm just going to use the built-in ones. So that's kind of fundamentally how Aurora works. And then when it collects all this data, you saw in our configuration file, we chose to log it all to this Aurora alerts.json.log file, right? So now we have these beautiful logs in JSON. And what we can do is we can forward those logs to Wazza, right? Now we can view those alerts in Wazza. So Aurora will take this information from ETW. It'll apply these rules on it, kind of like Sysmon. Sysmon has these rules that it uses to determine whether to log something or not. It'll then log it to this file, and then we can choose to forward logs from this file to Waza, so eventually everything ends up in Waza.
So you're running Aurora on Windows Server 1.
On all of them. On all the Windows servers, we have an Aurora agent running. Yep. We have the same setup. And you can see in my, just to like fully prove this point out, if we go to my Waza, remember the OSSec agent folder is responsible for Waza. If I go to my configuration file here, ossec.conf, you can see here are all the logs that I'm choosing to forward to Waza, and that includes this Aurora alerts log file. Make sense? Let's see, I'll go a little bit. I don't want to go too long, but I will go.
So it's not actually possible for Waza to interface with ETW directly.
No. Fundamentally, Waza is a SIM. A SIM just takes logs from different places and interprets them. A SIM is not something that interacts with ETW or like on the low level like that. ETW is kind of special in that you have to like create what's called a consumer and attach that consumer to ETW and then get, I don't know, it's a whole thing.
So Aurora collects logs from ETW and
Yes.
adds Sigma rules.
Yes.
And then send those logs to SIM.
Yes. Mm-hmm. Correct.